So today we're going to see the solutions. We have been doing the modeling and we're going to start with the solutions now. And to be able to start with the solutions, we need to know what the solutions are. What kind of solutions can we have in a given model? Now the first one is the, let's say the most common one, I guess, at least in our, course, but it might not be that common normally, but still it's the most common in our course. It's the unique optimal solution. So there is a single set of values. What's a set of values? Think about it. We have seen that we can have different number of decision variables, x1, x2, x3, etc. For example, if you have 4 decision variables and if each of them could have, like, say 5 different values, then you will have 5 times 5 times 5 times 5 to the power of 4 different solutions. So one single set of them. Okay, it's like the theory of probability counting counting course. So you pick any one of them and you say that, okay, this is the optimal solution, unique optimal solution. So that is the solution that gives you the best possible answer. Either it's maximization or minimization, doesn't really matter. But that one solution gives you the best possible answer. Okay, you can have alternative optimal solutions. When you have alternative solutions, it means that you have actually more than one solution that gives the same outcome, same value for your z, for your model, okay, for your maximization or minimization. Now this says that this is actually not just more than one, it's infinitely many, but they all give the same solution, which you will see what I'm talking about soon enough. At least on graphic it's easier to understand. You can also have an infeasible LP, which means that you cannot find any solution that actually satisfies all your constraints. Now, this means that your constraints are conflicting, okay? At least one of them is, conflicting with others, so the model has no solution. You cannot find a, possible solution that satisfies everything, so there is no solution. Or you could have an unbounded LP. In this case, your solution can go to infinity, either plus or minus, but it's usually plus infinity, which we'll see, but still it can go to infinity. It's not bounded at least on one side, okay? It may be bounded on more than one side, but it can be unbounded. It can go to infinity. You can say that, okay, this is a maximization problem and the maximum value is at infinity, okay? You can pick your x values however you want and you can keep changing them and you can keep increasing your z value all the time, which means that it's unbounded. So these are the 4 types of solutions you can find in an LP, and at least one of them, not at least, but exactly one of them should be there, okay, for each model. So we have a few important parts, a theorem for the linear programming. It says that if a solution exists to a bounded linear programming model, then it occurs at one of the corner points. Now, the corner point is the intersection of 2 linear constraints. For a linear program model, of course, 2 linear constraints, and the intersection, the corner point, is, if there is a solution, then at least one of those corner points is part of that solution. You can have more than one corner point with the solution, which was the alternative solution, which you will understand when you see the graphs, but still, there's at least one corner point that is the optimal solution when you're talking about the bounded linear programming problem. If a feasible region is unbounded, okay, then a maximum value for the objective function does not exist if it's unbounded on the maximum way, okay? It might be unbounded negatively, but still, if it's unbounded negatively, it's still going to be bounded somehow if your, x values are positive anyways, at least not negative anyways. But still, if a feasible region is unbounded, then a maximum value for the objective function doesn't exist. So it goes to infinity. This is what it's talking about. If it's unbounded, it goes to infinity, all right? If a feasible region is unbounded and the objective function has only positive coefficients, then a minimum value exists. Yeah, that's logical, because if it was unbounded and if it had the objective function had negative coefficients, then it could have gone to negative infinity as well. But in here, if all coefficients are positive for the objective function, that goes to positive infinity, so it cannot go to negative infinity, so there should be a minimum value, which is usually 0 at this point, but still it might not be. We will see the counter examples as well. So these are the fundamental theorems, but this isn't that important right now. You don't need to memorize all this stuff. You just need to know it as a general knowledge sort of thing. But this one is the important one. Types of variables. We have two types of variables, and we will keep using their names all the time. Basic and non-basic variables. Now, with basic variables, we are talking about variables that are in our solution. Okay. So, for example, then again, we have x1, x2, x3, and x4, four different decision variables. And from these four different variables, a solution we have found gives us x1 is equal to 2, x3 is equal to 4. Okay, x1 and x3. Now, these two variables have non-negative values, and the others have values of 0, and we know that they are not in the solution. You may have a value of 0 and be in the solution. That's possible. We will talk about it later. That's a degenerative situation. But still, if you have a value of non-negative value, especially a positive value, then you're in the solution and you're a basic variable. If you're not in the solution, if you don't take any positive values and you're not in the degenerative variables, so you are not in the solution, then you're a non-basic variable. This is an important distinction: basic and non-basic variables. If a variable is basic, it's most probably has a value of greater than 0, which is a positive value. If it's non-basic, it has to have a value of 0. That's for sure. So basic variables are in the solution, non-basic variables are not. And another type of distinction, that's for the constraints: binding and non-binding. Now, binding constraint, it's also called an active or tight constraint. A binding constraint, think about the constraints. There's a left-hand side with values of x and coefficients for x's, and there's a right-hand side, a scalar value, like 2x1 plus 5x2 is less than or equal to 15, for example. If it's a binding constraint, then the left-hand side should be equal to right-hand side. So the x values should give a total of 15 for the left-hand side. Okay, if the right-hand side value is 15, then the left-hand side should be 15 as well for a binding constraint. For a non-binding constraint, there might be a slack or an excess value there. There might be a slack or excess value there because it allows to be less or greater than the right-hand side. If the sign is, then again, less than or equal to 15, then the left-hand side could be 14, 13, 20, I don't know, 12, 9, 8, whatever. It can be less than 15 if it's non-binding, but if it is binding, then it should be equal to 15 anyways. So these are the definitions we need to know when we are going into solutions. What about the solution type? Now we have a graphical solution. In the graphical solution, all we have to do is just graph the constraints and the objective function properly. But to be able to graph a solution, you must have two decision variables. If it's more than two decision variables, then it's not, at least with more than 3, it's not graphable, because every decision variable represents a dimension. With just one decision variable, you have a line. With two decision variables, you have a plane, an x and y. You can think of it as an x and y. With 3 decision variables, well, you have a space, x, y, z. With 4 decision variables, you can have a hyperspace, and it goes on like this. So it's getting bigger and bigger, but you cannot graph on 4 dimensions, and you cannot even graph on 3 dimensions by hand. It's not that easy. Some of us might have that capability. I know I don't, but still, with 2 dimensions, everyone should be able to graph it because it's just lines on 2 dimensions, so it's easy. With 1 dimension, you don't need to graph anything because it's just a number line, so you just check them out. It's easy. So when we're talking about a graphical solution, we are talking about solutions on 2 dimensions, which means that we have just 2 decision variables. Now, the graph will show us the feasible region. The graph will show us all the edges and corners. The graph will show us the objective functions, positioning, which means it's you're gonna see how it positions itself between those edges and corners. You're gonna see what I'm talking about in a minute. But still, the objective function, think about it. When you graph on a plane, you know the numbers. For example, ax plus b is equal to y. For any a and b and y value, you can just graph it somehow, okay? But with the objective function, you don't have the b value. You just have ex minus y is equal to something. We don't know what that something is. We are looking for that something, okay? We don't know the value. We are trying to maximize that value. So with the objective function, you have to be able to graph it, loosely, because it can move. You will see what I'm talking about in the example soon. So as you move that objective function up and down or left or right, depending on how it goes, you can find the optimal solution from the graph. How do we do that? Let's start with an example. Now, we have a breakfast example, which is actually pretty easy to model. Let's see. A health-conscious family wants to have a very well-controlled vitamin C-rich mixed fruit breakfast, which is a good source of dietary fiber as well. Okay, in form of 5 fruit servings per day. They choose apples and bananas as their target fruits, which can be purchased from an online vendor in bulk at a reasonable price. Okay, so we have 2 types of fruit servings, which is bananas and apples, which will be our objective function decision variables, or the constraint decision variables. The decision variable will be from choosing apples and bananas. Probably how many servings of them you will see. Bananas cost 30 rupees per dozen. Okay, 6 servings, 30 rupees. And apples cost 80 rupees per kilogram, which is 8 servings. Okay. Given one banana contains 8.8 milligram of vitamin C and 100 and 125 grams of apples, which is 1 serving, contains 5.2 milligrams of vitamin C. So this is the amount of vitamin C we have from 1 serving. Okay. Okay, what else? Every person of the family would like to have at least 20 milligrams of vitamin C daily, but would like to keep the intake under 60 milligrams. So our constraints are the intake values. It should be between 20 and 60. How much fruit servings would the family have to consume on a daily basis per person to minimize their cost? Okay, so we already know that each serving of one banana contains 8.8 milligrams, and 1 serving of apple contains 5.2 milligrams. So 1 banana, 1 apple, you can think of it like that. So 1 banana plus 1 apple, 5.2 plus 8.8 is going to be 14 milligrams, for example. Or 2 bananas plus 1 apple, or 2 apples plus 1 banana. We can mix and match any way we like. We can do this any way we like. But we want to make sure that we get at least 20 milligrams of vitamin C and at most 60 milligrams of vitamin C. Okay, so each banana costs, 6 servings of them cost 30 rupees, so 30 over 6, 5 rupees. All right, each apple costs, so 8 apples cost, 8 servings of apple costs 8 rupees, so each apple would cost 10 rupees. So we have 5x plus 10y. X is for bananas, y is for apples. Okay, so apples are pricier than bananas. It might be. And we also know that we need to have at least 20 milligrams of vitamin C and at most 60 milligrams of vitamin C. So 8.8 times x plus 5.2 times y. So 8.8 is for the banana, 5.2 is for the apple. This should be greater than 20 and less than 60. So this is how we're going to model this one. I know that it's not that easy to model it in your head, but if you keep writing them down, you can model it easily enough. So this is the model we are trying to solve. It's a minimization model because we are trying to minimize our cost. What we need to do to solve this is just graph it. Okay, we need to graph this. So what are we going to graph? This is one line, 5x plus 10y. Okay, this is another line, 8.8x plus 5.2y is equal to 20. Start with equality. Then, according to your sign, the greater than or less than sign, you're gonna just let's say color above or below the line. Same for here. 8.8x plus 5.2y is equal to 60. Okay, let's start with drawing. So as you can see here, this is the 8.8x plus 5.2y is equal to 60, and this is 8.8x plus 5.2y is equal to 20. So we already know that, let's go back, we are looking for greater than 20 and less than 60. Greater than 20 is going to be the area above this line, and less than 60 is going to be area below this line. So we have this part, as you can see over here, all of here, as our feasible region. And then we are looking for the minimization of 5x plus 10y. So to minimize this, we have to move this line. As you can see, this is just 5x plus 10y is equal to 50. Why equal to 50? Because it's easy to draw equal to 50. But this equal to 50 is not our optimal solution. This is just one feasible solution. Okay, we're going to move this line up and down depending on the optimization, direction. As this is a minimization problem, we're going to move this line down to minimize this 50. Okay, as we move it down, this will get minimized, and we're going to check where this line touches the feasible region last before leaving it. So you can think of it like this. As you move the line, as long as you're inside the feasible region, your solution is a feasible solution. It can happen. You can just choose your x and y like that. If this line leaves your feasible solution, then that solution isn't feasible anymore, and you cannot pick those values. You cannot choose those values. So as I minimize this one, I could just go below, this axis, and I could say, okay, I'm making money from not buying apples and bananas, but it's not possible. You have to stay in this region. So when you are going down, this point is the last point that you are touching the feasible region. So this point P is your optimal solution. Now this point P has values y is equal to 0, which can be seen from here, and x is equal to 2.27. And when you put 2.27 into your objective function, you get 22.7. Whatever, x is 22. Oh, sorry, when you put it here, you're gonna get 11 point something, 11.35. So this will be your minimized cost. So let's go back. This is your objective function. It's set at a value, any value, it doesn't really matter. And you start going up and down. You could have set it at a different value. The the line wouldn't change its direction. Okay, it will always be like that. So you can go up or down, it doesn't really matter. And even when you go down, you can see that this is the last point you are touching this feasible region. Check out here. This is your feasible region here. Let's just annotate it to see it easier. Where is that drawing? This part over here. Oops, it's gone out, but still you can understand what I'm talking about. This part over here is your feasible region. So the line is going out over here. So it cannot go any lower. If it goes any lower, it will not touch the feasible region. So this is the optimal solution you can find for the minimization. If this was a maximization, it would try to go up, and it would probably touch it over here somewhere. So that will be your maximum point you can find with this model. But as it's a minimization problem, it has to go lower, and it is the place where you leave the feasible region. So this is your solution. But this is just the minimization. It's the first time we are seeing it. Let's check out something we already know. Gepetto's wood carving model. Now, we remember this one from the first week. We have been talking about this one for some time now. This is your objective function. You are trying to sell soldiers and trains, if you remember that one. And these are your x1 are your soldiers, x2 are your trains, number of soldiers and trains you are producing and trying to sell. And these are your constraints: finishing, carpentry, soldier demand, and the sign restriction, of course. Now, these three constraints, they have to be graphed. Okay. If we are trying to find a graphical solution, we have to graph these three and then the objective function. Okay, let's graph them and see. Now, this one is a demand constraint for the soldiers. This is the carpentry constraint, this is the finishing constraint, and these are isoprofit lines. Now, isoprofit lines, as you can see, are your objective function lines. These are all objective function lines, and they all have the same type of, objective function: 3x1 plus 2x2. The equal part is different. It can be equal to 50, 100, 110, 80, for example, 60, 100, 180. As you can see, they are different lines. Okay, but still, they are all the same objective function: 2x1 plus 3x1 plus 2x2. Now, this is the feasible region, the shaded area over here, yellow. Now, this feasible region gives us 1, 2, 3, 4, and 5 corners. We already know that our solution should be on one of those corners. We have talked about this on the theorem. So, as this, objective function has to be maximized, we're going to take it up and up and up and see how that z value changes and where it touches the graph last. And as you can see, as this one goes up and up, this G point is the last point that the objective function is touching the feasible region. So this G is the optimal solution. And it has a value of 180. Now, this G can be, we can find this solution by intersecting these two constraints, the finishing constraint and the carpentry constraint. So what I have to do is just, these two constraints are binding now, because at this point, both of them are satisfied. And this demand constraint is non-binding, because we are not on this constraint right now. Can you see what I'm talking about? When we are talking about binding and non-binding constraints, we are checking to see if the solution is on that constraint. Now, 4-point G, we don't know if it's optimal or not. We don't care about it right now. But 4-point G, the finishing constraint and the carpentry constraints are binding constraints. But the demand constraint is not. For example, 4-point F, the demand constraint and the finishing constraint are binding them, but the carpentry constraint isn't. Okay, so 4-point G, then let's go back and find the solution. 4-point G, the finishing constraint and the carpentry constraint. This means that this value is an equality now, and this value is an equality now. So from these two equalities with two unknowns, we can find x1 and x2. You remember this one from a previous mathematics courses, I guess. So what you have to do is just, for example, for this one, just subtract this from each other. So if you subtract both of them, the bottom one from the top one, you will get x1 is equal to 20. If x1 is equal to 20, then x2 is equal to 60. So 20 to 60, which you can see here already, 20 to 60 is our optimal solution. x1 is equal to 20, x2 is equal to 60. This is the optimal solution for this graph. So each point for each of these 5 points, 1, 2, 3, 4, 5. There's even a 6th point here, but it's not in the feasible region. There's a 7th point, 8th point, 9th point, but they are not in the feasible region, so they don't count. Only 5 points on the feasible region, 1, 2, 3, 4, 5. So you can find the solution for each of these 5 points and then just compare which one is higher. That's the way as well, but this is easier. But still, if you're not good at drawing, if you are, thinking that you might have made a mistake there, just calculate every other value you can find that's relative at least, and you can just find the solutions for each of them, that values for each of them, and then compare. But still, this is for small models, not with big models. No, you cannot do it with large scale models. But still, with small models, you can just find every value for each corner and then come to the solution from there. What about the minimization model? For example, the Dorian Auto. We remember this one. They are trying to sell their automobiles to high-income women and men, and they have to find the minimum costs for advertisement. So they're trying to find which advertisement type to buy. And we had, I think, football matches and operas, soap operas, I guess. So X1 and X2, we are trying to minimize the cost for X1 and X2.
Tamam, bir şey sorabilir miyim?
Tabii ki.
Mesela types of constraint'leri yaparken binding olarak direkt tanımlayabiliyor muyuz, yoksa hani şu noktaya göre şu constraint binding?
Noktaya göre binding oluyor. Mesela G noktasında finishing ve carpentry binding. D noktasında sadece carpentry binding. F'te demand ve finishing binding. E'de sadece demand binding. Hani her noktanın o noktayı kesen constraint'leri binding oluyor. Eğer o noktayı kesmiyorsa binding ne demek bu? O noktadan uzakta bir yerde demek diğer non-binding demek. Mesela bakın G noktasına bakın. G için dedik ki finishing ve carpentry binding. O zaman demand G'den uzakta olmalı. Evet, demand hakikaten G'den uzakta. G'den demand'e bir dik uzaklık ölçerseniz bu pozitif çıkacaktır demek oluyor ki öyleydi. G'den demand'e bir pozitif dik uzaklık var. Veya F'teyken demand ve finishing binding ise o zaman carpentry'nin dik uzaklığı var. Evet, F'ten carpentry'nin bir dik uzaklık var. O yüzden carpentry binding değil diye biliyoruz.
Anladım hocam.
Bir şey değil. So, back to Dorian Auto. Now, with the minimization, we already have, okay, these signs are wrong. This should be greater than and greater than, but we have two constraints and a minimization tool model. Now, to be able to, again, graph this, we have to start with assuming they are equal and graph those equalities and then just draw the, feasible region from the sign type. But again, as I said, this should be greater than and greater than. These are wrong. But still, we know that there are no problems there. So we have to just find and graph those values. Okay, how do I start graphing this constraint? For example, here's one. 7x1 plus 2x2 is equal to 28. You have to pick and choose one of those x values and make it 0 and start with the other one. For example, if x2 is 0, then x1 is equal to 4. If x1 is 0, then x2 is equal to 14. So I have to go from 4 to 14. Let's see that. As you can see, 4 to 14. This is the high income woman. This one. And what about this one? Okay, if x1 is 0, then x2 is 2. If x2 is 0, then x1 is 12. So from 2 to 12 or 12 to 2, however you choose, 12 to 2, as you can see. So these are our constraints. These two are our constraints. And we know that these are greater than signs. This is wrong here. So these are greater than signs. So we have to just shade above it, just color above them. So as you can see, actually these two constraints and this feasible region is unbounded. It can go to infinity, but it's a minimization problem. So what we need to do is find out where this objective function leaves our feasible region at the bottom when it's going down. So this is z equal to 600, this is z equal to 320. There are other values, of course, but they are all parallel to each other. So we just have to find those parallels and find the least amount of cost we can find when we are drawing those parallels, which is at point E. So there are actually three different solutions we can find, B, E, and C. There's, of course, the unbounded one, but it's a minimization, so it cannot be unbounded. And we are finding the E value as the minimum value over here. So at C, it's at, for C, it's 600, for E, it's 320, for B, it's something much higher, I guess. So 320 it is, so E. So, which means that we have to find the solution from those two constraints intersection point. Let's go back and try to find. So we know that these two should intersect, so we can just multiply the top side with 6, I guess, and then subtract it from each other. Or yeah, that's the best way, I guess. So when we subtract it from each other by after multiplying this part by 6, we're gonna get a high value. It's gonna be big value, but these x values should be in total 320. Okay, we're gonna find x1 and x2 after multiplying this one by 6, and that x1 and x2 is going to give us 320. Now, this is graphical solution. It's pretty primitive and it's useful because it's fast if you can, draw fast and calculate fast. But it's extremely primitive and extremely, let's say, limiting because you cannot do it if it's more than 2 decision variables. It can only work with 2 decision variables. While it's useful, as I said, it's limiting and primitive. So it will be useful to understand how solutions work, okay? Because you can see the graphs and you can understand how constraints work, how the objective function moves, etc. And in the next parts, you will see how simplex works on it, because it's going to give us a clear picture of how simplex moves. But still, it's extremely primitive. But then again, it can be used with 2 decision variables, and there are ways of converting to 2 decision variables, which you'll see further down the road. But still, this is the most primitive solution we have at our hand. And after we start seeing larger and larger models, and we have simplex algorithm in our belt, we will not be, using this anyways. But as I said, it's extremely important for understanding how this thing works, how our models work, how the solutions work. So, yeah, this is where we start the, solution models, solving those models. Z değerlerini nasıl bulduk onu kaçırdım diyorsun. Tamam, güzel. Hadi yapalım o zaman uzun Türkçe anlatarak yapayım onu. Daha şey olsun, fark etmiyor çünkü çok bir şey yok ama. Şu ilk kısmı 6 ile çarpın. Şurayı 6 ile çarpın. 7x1 artı 2x2 küçük eşittir 28. Bunu 6'ya çarparsak ne geliyor? 42x1 artı 12x2 eşittir'e döndü bu arada bunların hepsi. 28 çarpı 6 kaç yapar? Var mı elinizde hızlıca çarpabilecek biri? Ben de çarpayım bir yandan ama. 168. Güzel. 168. Şimdi ne diyorduk? Kısıtların çarpılması kısıtların şeyini değiştirmiyor. Bunu istediğimiz kadar çarpabiliriz. Boyutunu değiştirebiliriz, büyütebiliriz, küçültebiliriz. Şeyi değiştirmez. Hani kısıtın çizildiği şekli değiştirmez. Yani şu 42x1 artı 12x2 eşittir 168 ile şu ikinci tarafta çizdiğimiz, bir saniye bunu geçelim yan tarafa, oradan göstereyim. Şurada çizdiğimiz şeyin hiç farkı yok. Bakın şimdi. Türkiye'ye gel. 7x1 artı 2x2 eşittir 28 ya bu. Ne diyorduk burada? 4'e ve 14'e bakacağız diyorduk. Yani şuna bakacağız diyorduk. Şu kısma bakacağız diyorduk. Şununla, şu çizdiğimizde bunu açıp çizsek çizeceğimiz şey aynı. Hiçbir farkı yok. İstediğimiz gibi çarpabiliriz o yüzden. Bir de çarpıp büyüttük. Niye büyüttük? Şu 12x2'leri sadeleştirmek istiyorum. Yukarıdakinden aşağıdakini çıkarsam ne geliyor? 40x1 eşittir ki aşağısı eşit artık. Çünkü binding olarak bakıyorum noktayı bulmak adına. 144. Değil mi? 40x1 eşittir 144 geldi. İşlem hatası yapmıyorsam eğer. O zaman x1'in değerini bulmam gerekiyor. 144 bölü 40 diyeceğim. x1'in değeri 3.6'ymış. Şimdi x1 3.6 ise y'ine koyacağım. 3.6'yı 7 ile çarpalım. Çarpı 7 diyelim. 25.2. 28'den çıkartalım. 2.8. 2'ye bölelim 1.4. Yani x2 eşittir 1.4 oldu. 3.6'yı 1.4 olarak bulduk. Bunları yerine koyacağız ve oradan bize bir çözüm getirmesini isteyeceğiz. O gelen şeye göre de değere göre de bakacağız. Şimdi 1.4'ü koysam 2.8, 3.6'yı da üzerine ekleyeceğim şeklinde bir şey var, çözüm var. Ha, şurası hatırlarsanız sadeleştirilmiş hali. Bu büyük ihtimalle 50 katı, 500 katı falan gibi bir şeydi. O yüzden o 50 katı ya da 500 katı çarpmamız gerekiyor şuradaki 320 değerini bulmak için büyük ihtimalle. Bu sadeleştirilmiş hali. Bu sadeleştirilmiş halini kullanıp hani direkt bunu koyup yerine 3.6'yı ve 2.8'i koyup 6.4 çıktı. 6.4 çıktı değil mi? Evet. 6.4 çıktı da diyebilirdik ama büyük ihtimalle dediğim gibi bunun bir 50 katı falan da o. 50 çarpıydı yani. Çünkü bunlar 50'ye 100'dü diye hatırlıyorum maliyetleri. Ama bu sadeleştirilmiş hali. 6.4 yerine 320 demiş. 50 katının konmuş halini burada bize söylüyor. Biz burada sadeleştirilmiş 50'ye bölmüş halini koymuşuz. Aynı şey. Ne demiştim? Şu değerlerin katsayılarıyla oynayabiliriz. Aynı oranda arttırdığımız veya azalttığımız sürece sonuçta eğimi değişmez hiçbir zaman. Her zaman aynı eğimde kalır. Fakat z değeri veya burada w değeri değişir. Biz burada 6.4 bulduk fakat 50 katı olarak alsaydık 320'yi bulacaktık yine. Farklı bir şey bulmayacaktık aslında. 6.4 yerine sadece 320 bulmuş olacaktık 50 katı olacağı için. Ama burada mesela şu yerine koyduğumuzda 50 katını almadığımız için şu an henüz daha bunun 6.4'ü buluyoruz ama aynı çözüm bulmuş oluyoruz. Farklı bir şey gelmiyor aslında. Aynısı öncekinde de geçerliydi. Peki bu bir tanesi. Dedik ki burada 50 katına bakıyoruz. 50 katını kenara koydum biliyorum. Peki B noktasını bulalım hadi. B noktasının cevabı ne? B'nin çözümü ne olur? Zaten burada x1'i bulmuşum ben. 0. X2'yi de bulmuşum 14. O zaman x2'yi yerine koyacağım. 2 çarpı 14'ten 28. 28 çarpı 50 gelecek. Çok büyük bir rakam. Peki aşağı bakalım. C noktasına bakalım. C noktasının değerine x1 bu sefer 12 alıyor. X2'nin değeri 0. 12'yi yerine koyacağım. 12. 12 çarpı 50 600 vermesi lazım. 600 veriyormuş zaten. Hani farklı bir şey yok. Ha bunu 600 değil de ya 12 bıraktım olmaz mı? Olur. 50'ye çarpmak zorunda değilim. 50'ye çarpacağımı bildiğim için çarptım. Modeli sadece böyle biliyor olsaydım, bunun 50 ile sadeleştirilmiş olduğunu bilmiyor olsaydım zaten 12 diye bırakırdım ve ben 6.4 diye bırakırdım. Ve yine derdim ki 6.4 12'den daha küçük. 6.4 de o cevap aslında. Yani yaptığım tek şey şu noktaların x değerlerini bulup o x değerlerini gidip burada yerine koymak. Okey?
Çok teşekkürler hocam. Tamamdır.
Var mı başka soru sana?
Hocam yani 50 ile birlikte çarpmadan yapsak yani
Olur, doğru
sadeleştirilmiş
olur,
halini.
sıkıntı yok. Doğru olur, sıkıntı yok. Yani
Grafik doğru olur yani.
grafik doğru olur, çözüm doğru olur, x değerleri doğru olur. Sadece z değeri eksik kalmış olur ama o anlaşılabilir bir şey. Sadeleştirip yaptığını anlattığın zaman sıkıntı yok orada. Hani onu biliyorsan, ne yaptığını biliyorsan bu da şuna dikkat etmeniz lazım. Gerçek hayatta bu böyle bırakılmaz tabii ki. Yani şu 320'yi görmesi lazım. Adama gidip 6.4 dersen nasıl bu kadar ucuz mu diye sorar sana. 320 beklerken 6.4 yazarsın eğer diye. Ama bu 6.4'ün 50 katıdır dediğin zaman ha o zaman okey diyebilir. Yani çözüm doğru. Bakın şeyi çok iyi dikkat edin. Solution and optimal value. Optimal solution and optimal value. These two things are different things. This is the important part. So I'm switching to English so everyone can understand it very well. Optimal solution is the values of x's, your x values. Okay, this is the solution. Optimal value is the value of your z or your w, whatever you are using. Okay, optimal solution will be the same however you change your model, however you upgrade or downgrade, upscale or downscale your coefficients, however you multiply or divide them, the x values, the solution will always be the same, but the value, optimal value, will change. Okay, at least if you change your w, okay, the coefficients of your w. You could have written 2x1 plus 4x2 here, same solution. 50x1 plus 100x2, the original one, same solution. It's always the same x values, but how your x values translate into your, optimal value, this is where it changes. Okay, the objective function, this is where it changes. It can be the same It can be different as well. It doesn't really matter. Because as long as you can just interpret it the right way, the way it has to be interpreted, it's okay. Alright? Yani şurayı ne kadar değiştirirseniz değiştirin. İsterseniz 10'la çarpın, isterseniz 20'ye bölün, isterseniz 500'e çarpın, fark etmiyor. Siz sadece optimal çözümün değerini, optimal değeri değiştiriyor olursunuz. O değerin veren çözüm, yani x şeyleri, x değerleri değişmeyecektir yani. Her şeyi, yani her katsayı aynı sayıyla çarptınız veya böldüğünüz sayı. Gidip de x1'i 5'e çarptım, bunu 3'e böldüm derseniz o zaman değişir tabii ki. Çünkü eğimini değiştiriyorsunuz şimdi. Bakın, şuradaki eğim önemli. Bu eğim nereden çıktığını gösteriyor feasible region'da. Okay? Bu eğime göre hangi noktadan çıkacağı belli oluyor veya hangi noktadan içeriye gireceği belli oluyor. Nereden baktığınıza bağlı. Dışarıdan başlayıp içeriye sokmaya da çalışabilirsiniz. İçeriden başlayıp dışarı çıkarmaya da çalışabilirsiniz. Tamamen size kalmış. Ama sonuçta eğime göre nereden çıktığı ya da nereden girdiği belli oluyor. O yüzden o eğim değişmediği sürece hep aynı noktadan gelip çıkacaktır. Yani x1 artı 2x2'nin eğimi de 5x1 artı 10x2'nin eğimi de aynı. Değişmez. O yüzden eğime göre bunun nereden gelip nereden çıktığı belli olacağı için, yani sadece z değeri değişeceği için o katsayılara göre nokta değişmeyecek, çözüm değişmeyecek demek oluyor. Any other questions?
Hocam burada z fonksiyonu her zaman bu noktaları kesmek zorunda değil mi?
Değil, çünkü z
O zaman
fonksiyonun
sonucumuz
eğimi değişirse başka yerde de kesebilir işte. Son kestiği yer neresi?
evet.
Z fonksiyonu sonuçta her yeri keser. Feasible'deki her yeri kesebilirsin z fonksiyonuyla. Çünkü o fonksiyon sonsuza gidiyor aslında. Şuradan bakın devam ediyor böyle. Ha, eksi değerleri kullanmıyoruz. Evet kullanmıyoruz ama olsun. Sonuçta bunu en küçüğe getirsen de buradan sonsuza kadar götürebilirsin bu z fonksiyonunu aslında. Yani orijinden başlatabilirsin o z'yi. Orijinden sonsuza kadar gidebilir o z. Sonuçta x1 ile x2'ye 0 verirsen orijin noktasında oluyorsunuz z fonksiyonu olarak, otomatik olarak. Oradan dışarıya doğru şu eğimle, bakın bu eğimle dışarıya doğru ve sonsuza kadar götürebiliyorsun. O yüzden her noktaya dokunabilir z fonksiyonu. Ama optimal çözüm bir tanesinde oluyor. Ha, bazen birden fazla olabiliyor. Nasıl birden fazla olabiliyor? Mesela diyoruz ya, alternatif çözüm olsaydı. Alternatif çözüm şu demek. Senin z fonksiyonun buradaki kısıtlardan biriyle aynı eğime sahipse, o zaman mesela düşünün şeyle aynı eğime sahip olduğunu. Bu biraz zor olacak ama şu A'dan B'ye giden şu kısıt var ya, high income woman constraint. Bununla aynı eğime sahip olsa, yani o da buradan buraya geliyor olsa, o zaman kesişim noktası yine bu doğru parçasının tamamı olurdu. Ve doğru parçasının tamamı üzerinde her nokta, feasibility'de olan her nokta bir optimal çözüm noktası olurdu aslında. Yani şu B de optimal çözüm oldu, bu E de optimal çözüm oldu. Aradaki sonsuz tane küçük nokta da optimal çözüm olurdu. Alternatif çözüm de bu demek oluyor mesela. Yani İlla sadece bir tanesini kesmek zorunda değilsin. Sonsuz tane noktada da kesebilirsin tabii ki sen şeyi. Bu da sana alternatif çözüm vermiş olur. Ama en az bir noktada kesmen gerekiyor tabii ki bu feasible region'ı. Bir de tabii ki feasible region olması gerekiyor. Feasible region yoksa zaten direkt infeasible oluyorsun. Olursuz oluyorsun yani Türkçesinde. Anything else?
Teşekkür ederim hocam.
I keep switching to Turkish all the time, but still, if your objective function is parallel to one of your constraints, then that constraint, every point in that constraint that is inside the feasible region becomes a solution point as well, optimal solution point as well. This is the English version, the short version of it. Okay, anything else?
Hocam burada peki z eşittir 600'ü göstermemizin bir şeyi var mı yani? E noktası minimum nokta. Onu bilmemiz gerekiyor.
Evet.
Ama 600 ne işe yarıyor?
Göstermek için sadece, yani şart değil.
Göstermek.
B'yi de hesaplayabilirsiniz. B'yi de hesapladık az önce. C de hesaplanabilir. Ama diyoruz ya, hani E zaten optimal. Bunu biliyorsak sadece bunu hesaplamak yeterli. Ama çiziminize güvenmiyorsanız, ya ben eğimi düzgün tutturamayabilirim, şeyi düzgün çizemeyebilirim. Hani sonuçta çizmek de kolay bir şey. Kalem kağıt kullanmıyorsanız çizmek o kadar şey değil. Yani kesin bir şey değil. O yüzden hani çizime güvenmiyorsanız şey diyebilirsiniz. Ya ben bir C'yi de hesaplayayım, garanti olsun. 320'den büyük çıktığını göreyim ki şey olmasın, hani yanlış olmasın. B'yi de hesaplayayım, yanlış olmasın diyebilirsiniz. Yoksa E noktasına eminseniz, grafiğinizi doğru çizdiğinizde E noktasına hesaplamanız yeterli zaten şeyi görmek için. Optimal çözümü görmek için.
Tamamdır hocam. Teşekkürler.
Bir şey değil.